An angle is what happens when you have two rays. Rays start at a point, but then continue on into infinity. Lines go to infinity in both directions. Line segments start and end at points. All right? So, big differences. When you have two rays that come out of the same point, though, well, there are two angles between them. Generally, for our purposes, we look at the smaller of the two angles because, guys, if you fold a piece of paper back in on itself and then you let it fall open, well, you can measure what's between those two pieces of paper, the two ends of the paper, or you can measure around the outside. So for our purposes, we measure the smaller one generally. If you measure around the outside, that would be a reflex angle. Reflex angle. If you have an angle that is 90 degrees, we call it a right angle, and we mark it like this. Unless it's stated to be 90 degrees or you see this marking, do not assume what looks like a right angle is in fact a right angle. Now, a right angle is 1/4 of the way around the 360 degrees of a full turn. A circle is divided into 360 equal parts. So if you turn in a circle, you have turned 360 degrees. If you turn more than one full circle, you have turned more than 360 degrees. If you turn halfway, like say from facing this way to facing the exact opposite way, that's 180 degrees. Now this looks like a straight line. It is a straight line, but it is also a straight angle. Like we assume that there's some point marked in the middle here. Obtuse angles are between right angles and straight angles. Acute angles are less than right angles. Now, if you have two angles that are right across from each other, made of two lines that cross, as opposed to a ray coming out from this point and another ray coming from out this point, that's an angle, okay? But what if you have two lines crossing? Or you can say that this is four rays. It's just that two rays in the opposite direction are kind of the same as just one line, assuming they cross the same points. So, if you are in the United States, you may call opposite angles like this one and this one, or these two. Opposite angles are the same because, well, your straight line is a straight angle. This is 180 degrees, okay? So if you take 180 degrees here and 180 degrees here, and you subtract the same amount from both, what happens? We know that if we subtract the same amount from two equal amounts, we end up with still two equal amounts. It's like we have two boxes of candy that have the same number of candies in them. We took 5 from each box. The boxes are still equal in the number of candies. It's just a little bit less than it was before. Now, if you are in the United States, you may call these angles that are opposite to each other vertical. The rest of the world generally refers to these as just opposite angles because it's way more obvious what you're talking about. These two angles are opposite from each other. Right? Yeah, the whole vertical thing that you can see sometimes in the United States can be attributed, as with many other things, to Americanceptionalism. Now, two angles that share a common side and do not overlap with each other, like say this angle here and this angle here, these two angles are adjacent because they're right next to each other. Now, what happens if they do overlap, such as this whole thing and either one of these? Well, they are not considered to be adjacent angles because of the overlap. Even though they have a common vertex, which is the tip of the angle, and one shared side with either one of the smaller angles. Now let's classify some angles. Classify each of these angles as acute, obtuse, right, or straight. Now, right angles are usually pretty visible. One of the sides will be usually flat on the page and the other one will be vertical, but they may not be. Is this a right angle? Well, if you need, you can actually tilt your head to look at these things, and that is still perfectly reasonable because, well, let's say you make a hand gesture or something. You can't guarantee that your hand gesture is actually a right angle, whereas the human brain is very, very good at, once we have something lined up with our horizontal plane of vision, the human eyes see way further out to the sides than they do up and down. When we have something lined up with our horizontal plane of vision, it's very, very easy to see if something is roughly vertical compared to that horizontal. So in other words, if something is perpendicular or at a right angle to that. So here we would see that, no, it's not. This is acute. And here, yeah, it's very clearly, we can see that it's going to be greater than 90 degrees. So this is obtuse. Now, for geometry problems, you should never assume something that looks like a right angle is a right angle unless they tell you so, or it's marked with the little square symbol, like this. Look, it doesn't matter how ugly the diagram is. If it's marked as a right angle, it's a right angle. Geometry diagrams are often not to scale. Yeah, I said that earlier, that you should never assume it's a right angle. But, of course, if the problem is asking you to judge by eye whether it's an acute, obtuse, or right or a straight angle, yes, if it looks like a straight line, label it a straight line. If it looks perpendicular, label it as a right angle. Like say this, you could look at the vertex and what the lines are supposed to be, line up your horizontal plane of vision with one of the lines, and you will see that the other one is basically vertical enough that you can say, yeah, this is supposed to be a right angle, I think, and mark it as such for the current grade level. I mean, otherwise you would basically be going, you just told me to identify whether that thing we're seeing off the side of the boat is a dolphin or a porpoise. I need a reference book. No, you kind of just make a judgment call based on what you know of the things. Or you just asked me whether that's a crocodile or a monitor lizard, so a large lizard. Yeah, use what you know and make a judgment call. So, let's label some angles opposite or adjacent. Oh, well, A and B here are, they're across from each other. So they are opposite. This is why opposite is so favored over the American vertical thing. Yeah. Adjacent, angle C here and angle D share the same vertex and they share one side, so they are adjacent. Adjacent. Okay. Now let's classify these angles below as acute, obtuse, right, or straight. Well, this one is greater than 90 degrees. It's bigger than a right angle, so this is obtuse. This one is, yeah, it's pretty clear that this is supposed to be a right angle. This is smaller than a right angle, so it's acute. And this one just looks like a straight line, so it is a straight angle. Some textbooks may be nice enough to put a vertex somewhere, so put a point somewhere. Others are not, so if you're asked to identify an angle and you only see a straight line, yeah, it's a straight angle, guys. Let's label these angles opposite or adjacent. Oh, these two, they share a side and they have the same vertex, and therefore they are adjacent. These two, they share the same vertex. Their sides are continuations of each other. So they're made from the same lines and they are across from each other or opposite to each other. These, same thing, they're opposite. And these two, they are next to each other. Adjacent things are next to each other. More specifically, in this case, they share a side and they share the same vertex. And they don't overlap. Okay? Because, like, adjacent houses, unless they're townhouses or condos, don't in fact share a side. Well, the lot does, but yeah. So things that are next to each other are adjacent in everyday speech, but in angles, you have to make sure that it actually fits the right criteria, i.e. share the vertex and share the side. Now, let's talk about what happens when you add or subtract angles. Specifically, complementary angles add up to 90 degrees. Supplementary angles add up to 180 degrees. If you want to find a missing angle measure within, say, 90 degrees or 180 degrees, or within however many degrees, you have to do some angle subtraction. For example, we know that this is 90 degrees. 90 degrees equals 43 degrees plus x degrees. Okay, well then x degrees is equal to 90 degrees minus 43 degrees. You subtract 43 from both sides and you flip the sides in the same move. So this gives us 47 degrees. Whoa! This diagram, 43 to 47 is not a huge difference, but it looks so skewed. Why? Well, it's because in geometry class, it's the numbers you're told that matter. Diagrams need not be to scale. Now, let's say we have 110 degrees and x degrees, and added together, they're equal to 180 degrees. Depending on how competent you are, your teacher will most likely eventually let you get away with just going 180 degrees minus 110 degrees, because omitting the initial step that says they are supplementary. This actually depends on regional conventions, because in some places you're solving this problem based on the fact that they're supplementary, so you kind of have to state that. Yeah, to be safe, it's probably better to start with the 180 degrees equals 110 degrees plus x degrees. Or vice versa. 110 degrees plus x degrees equals 180 degrees. And then x degrees equals 70 degrees. All right, let's find some other values for x. Oh, hey, these two angles add up to 90 degrees, and one of them is 58 degrees. I wonder what x could be. It's 90 minus 58 degrees, which is 32 degrees. At some point, you will reach a point where you can just omit the steps altogether for problems like these. You are probably not there yet, and I don't recommend actually trying this. So, 56 degrees plus x degrees. Showing your steps is generally considered a good idea. And not showing your steps can be foolhardy. Of course, the rearrangement step, that's another story altogether. So, you can just subtract right away. 124 degrees. And here, you would go 85. Like, in terms of geometric proofs, you'd use the fact that they are supplementary, which means you do this, and then you could just go straight to x degrees equals 95 degrees. Now there is a problem here, guys. This looks like x to the exponent 0. Whoa! That's not what we meant. Because x to the power of 0 is 1, unless x itself is 0. How do we deal with this problem? Well, it says, find the value of x. Whoa, okay, that means we can use 71 plus x equals 90. We can omit the degree symbols. Gasp. Okay, so 19, x equals 19. Yeah. So here, 45 plus x equals 90, x equals 45. And here we have 82 plus x equals 180. X is 98. Yeah, so those are the values of x. This can get really nasty when you get up far enough that you're regularly doing exponents. If you make a mental slip up and go x to the power of 0, no, try not to do this. All right? If we want to use a pie chart, how do we use a pie chart? If we have a protractor and we're constructing it, we kind of have to measure the angle in the middle, right? So the angle that is occupied is determined by how many parts out of, not 100. 100 is percentages. A circle we divide into 360 degrees. Then that means how many parts out of 360, so a fraction over 360, that is occupied by a certain portion of the pie. Okay, what's the total here? Yes, I know the graph is already there, but I'll show you guys how you get there from this point. The total is 104 plus 59 plus 54 plus 222. So, 439. So the fraction of the total 104 over 439. You have 59 over 439. And 54 over 439. And 222 over 439. Okay, then. 222 divided by, recall 1, times 360 equals 182 degrees. So 182 degrees, approximately. 54 divided by 439 times 360 is 44.3 degrees, approximately. We're using 3 significant digits here. So recall 1 times 360 equals 48.4 degrees, approximately. 104 divided by 439 times 360 is approximately 85.3 degrees. If we had kept it down to tenth of a degree, we would have had a 0.1 here, which all these added up would look very wrong. As in, you would have ended up with 360.1 degrees. Which, of course, is not a full circle. A full circle is just 360 degrees. But that's because a lot of these had to be rounded up slightly, as per the rounding rules. So, yeah. Fortunately, this just happens to add up to 360. Sometimes you will find that your numbers don't quite add up to 360. But by that point, it's just like that, close enough. So, if you end up with anything significantly greater than the entire pi, so 360 degrees, or if you're calculating percentages, 100%, if it's much bigger, you did something wrong. If it's like about right, yeah, that's just rounding error, guys. So, you would plot 85.3 degrees, and you would write United States in that box, or that arc, fan shape. Terms differ depending on language. Sector of a circle. Yeah, there are many different phrases for such a thing. And then you would do the others in, well, apparently this is a pretty unusual order, guys, because usually you put either the largest category first or the other category last. Well, interesting choices were made, apparently, when the diagram was made. It's our turn now to make ourselves a diagram. Okay. How many people competed at the swim meet? Total? Total was 18 plus 2, which is 20, plus 7 plus 5, which is 12, so 32. Fraction. 9 over 16, 18 over 32, 7 over 32, 5 over 32, and 1 over 16. So, degrees, 9 divided by 16 times 360, 202.5 degrees. 7 divided by 32 times 360, 78.75 degrees. 5 divided by 32 times 360. 56.25 degrees. And 1/16, i.e. 360 divided by 16, we would have 22.5 degrees. Okay, 22.5 degrees. How much is that, guys? Well, we know that 45 degrees would be... You know what? Let's use a ruler for this thing. Of course, there is skill to be had in being able to eyeball a pie chart and say, oh, this is about right, or no, what is this? I don't even. For example, here, 22.5 degrees. What's that? Oh, 90 degrees? Half of 90 degrees is 45 degrees, and half of that is 22.5. Oh, okay. Hey, what's 202.5 then? Oh, that's 180 degrees, so half the circle, plus 22.5. Oh, we can eyeball that too. This part is a little bit more complicated, but yeah, this is basically where you should have gotten up to. Yeah. What else could you have used besides the, oh, this looks about right option? What's this? 7, 5, 2. What's 2 plus 5? Oh, that's 7. So, this line should have cut this section of the circle in half. And did it? Yeah, more or less. Okay, that's correct. Or as correct as our hardware allows. Now let's talk about triangles. Because hey, if we talked about angles, what happens if you have 3 angles that define a shape using 3 sides? So an angle between each pair of sides. Oh, that's a triangle. Like how a tricycle has 3 circles or wheels. So a triangle has 3 sides and an angle between each pair of those sides. The symbol is, well, it's a little triangle. I'm sure you remember triangles from earlier grades. The sum of the measures of the angles, the internal angle sum is 180 degrees. And you can use this to find a missing angle measure. For example, here, find the value of x in triangle ABC. You would go x plus 66 plus 52 is equal to 180. Well then, x is equal to 180 minus 66 minus 52. Doing this sequentially is unpleasant. So 66 plus 52 on the other hand, oh, that's 118. So this is going to be 62 degrees. Right? Technically speaking, no. Because here it says x degrees. So we would have to say x degrees equals 62 degrees. And you remember what I said earlier about the whole looks like a 0 thing, yeah? So, we try to avoid x degrees when possible. Now, triangles can be classified by the measures of their angles. An acute triangle has 3 acute angles. So in other words, all the angles are less than 90 degrees. A right triangle has 1 right angle. So 90 degrees, because the other 2 angles have to add up to 90 degrees, so neither of them can be 90 degrees. Otherwise, you end up with 2 parallel lines and the shape never closes. An obtuse triangle has 1 obtuse angle. Both of the others have to be acute for the angle sum to still be 180 degrees. because most of that 180 degrees is occupied by that one obtuse angle. Triangles with sides that are all the same length are called, they can also be called, the sides are congruent, because if you have lines, unlike more complex shapes, there are no angles involved. Lines are congruent if they are the same length. Congruent means exactly the same shape. It could be flipped over, it could be rotated, it could be moved around, but it's the same shape. So if the lines are all congruent, then it's an equilateral triangle. If two sides are equal or are congruent, then it's isosceles. But an equilateral triangle is also isosceles, just for any given pair of sides. Now, if a triangle has all the side lengths different, then it is a scalene triangle. This triangle here, we see that it has 120 degrees at one of its angles, which is greater than 90. So it's obtuse. And we see that two of the sides are marked using lines, using these little lines, as being congruent. So it's isosceles. Now, if this had been 60 degrees and then it said it was isosceles, then it would have been equilateral, because an equilateral triangle has 60 degrees and the two neighboring sides equal, which happens to make all the angles 60 degrees and all the sides equal. Because an isosceles triangle has the two equal angles at the ends of the equal legs. Now, let's find the missing measure in each triangle and then classify the triangles as acute, right, or obtuse. Well, here we have x plus 82 plus 75 equals 180. That means x is equal to 180 minus 77, because you can group the numbers a little bit to make the subtraction easier. 100 minus 77 gives you, so x is 23 by subtracting 80 and then subtracting 77. So x plus 90 degrees plus 43 degrees, or rather x plus 90 plus 43 is equal to 180. X is equal to 90 minus 43, which is 47. No degree symbol there. And here, x plus 40 plus 45 equals 180. So x plus 85 equals 180. X is equal to 95. Classify the triangle as acute, right, or obtuse. Well, here all the angles are smaller than 90 degrees, so acute. This one, we see that there's a right angle clearly marked, so it's right. We see that this angle is greater than 90 degrees, so this is obtuse. Okay, now let's classify each triangle here by the angles and by the sides. Here we see 50 degrees, 60 degrees, 70 degrees. All the angles are unequal, therefore this must be scalene. And they're all acute, they're all less than 90, which means acute scalene. This one has two sides that are marked as equal with a right angle between them, and therefore it is right isosceles. Isosceles. Here we have 30 degrees, 40 degrees, and 110 degrees. So there are no equal angles, therefore there are no equal sides. This is scalene, but we have one angle that is greater than 90, therefore this is obtuse. Scalene. Scalene. And here we encounter a curious event that is typical of, say, an Americanized curriculum. A reminder to the reader and the student to use their brain. So, use logical reasoning, which is a method of problem solving that uses inductive reasoning, which makes a rule after seeing several examples, or deductive reasoning, where you use a rule to make a decision. You can probably tell that the typical editor of an American curriculum may or may not have put this in here to remind themselves, right? Well, actually, no, because geometry is all about making rules after seeing several examples, or at least the people who originally did the research and came up with all the axioms, i.e. things that you take for granted, the rules. And you use deductive reasoning all the time as well. You use rules to make a decision. For example, all the angles in this triangle are unequal. Therefore, all the sides are also unequal because isosceles triangles have two equal angles at the ends of their equal sides. The angles that are not shared by those two equal sides. Okay, so that is why this section is actually in this chapter. Okay, the examples though are a little bit not very geometric. Well, the exercises aren't either. It's fine. Just remember that in geometry we use a lot of inductive reasoning where we get examples and then make a rule using those examples as evidence, or deductive reasoning where we make decisions based on rules. So Sherlock Holmes deduced that something happened. Technically speaking, a lot of that is actually induction. So he induced that some sort of pattern happens, right? Well, actually, it depends on the specific example because, Sherlock Holmes knows that after this many days, flies on a corpse will have maggots that are in this stage of development. And so he observes the evidence and he uses the rules to make a decision as to how many days it's been since the murder. Yeah, that is deductive. But there are still plenty of examples that aren't. So it's actually remarkably complicated if you think about it for too long. But for now, let's just get this over with. So let's use the formula distance equals rate multiplied by time. In physics class you would use v for velocity, v arrow rather for velocity because that has a direction, or you could use just v for speed. But hey, that's physics class, which is rather far into the future for you, hopefully. So, how far a car has traveled after 4 hours if it's traveling at 65 miles per hour. You can tell this is Americanized. But even in the rest of the Anglophone world, or in various other places, you can see all sorts of distance units per time unit. You just gotta adapt. So, distance is equal to rate times time. Now you gotta make sure that the units here are compatible. Because if they said 65 feet per minute, then gave you the time in hours, you have to convert. Otherwise, if you multiply, you get incompatible units problems. 2 hours, 130. 4 hours, 260. And the unit is miles. Let's use logic for some of these following problems. Now, presuming that the cost per call is constant. Wait a second, do we actually have to presume this? No. Why? It's cost per phone call. That means it's an average, which means that we can just divide the cost by the number of calls. So, $44.00 divided by 40 calls is equal to $1.1 per call. Yes, I am aware that money is usually written with the cents written out, like $1.10, but yeah, whatever. Okay, Sasha, John, and Freud play the piano, trumpet, and violin, but not necessarily in that order. Now, Sasha and Freud sit on either side of the trumpet player, which means that John is the trumpet player. John, trumpet, and Sasha does not play the violin. So that means Sasha plays the piano and Freud plays the violin. Actually, you could just go straight to Freud plays violin. And your answer would just be then, your statement would be Freud plays the violin. But I'm sure you don't want to see me scribble on the board any more than strictly necessary. So yeah, word problems, you're supposed to write statements where you basically just restate the question with the answer attached. Okay, quadrilaterals. If you have seen a quadricycle ever at any point, if you live in Europe, you might be interested in knowing that there is actually a quadricycle classification for vehicles on roads, and some mini cars actually fall into the quadricycle classification, even if, like the POP 50, they PO, as in PEEL, P50, they actually are tricycles, like three-wheeled cars. They're still counted as quadricycles for legal reasons. Here, though, we are not, in fact, rules lawyering. We are doing serious logical math stuff. None of that legalistic stuff. So, quadrilaterals. Quad means four. Lateral means side. Quadrilaterals have four sides. Now, they can be classified using their angles and their sides. The best description of any particular quadrilateral is the most specific one you can think of. If you have one pair of parallel sides or more, it is a trapezoid. If you have a trapezoid that also has the other pair of sides parallel, then you have a parallelogram. If you have a parallelogram that has all the sides equal in length, it's a rhombus. If you have a parallelogram that has the opposite, all the angles being right angles, then you have a rectangle. In a parallelogram, the opposite angles are equal, by the way. And if you have a rhombus that has all the angles being right angles, or if you have a rectangle that has all the sides equal, by the way, this here is supposed to actually be two lines, but it's a little bit close together, so I'll draw it on for you. Here. This one actually, it's clear that it's two lines. Okay. Just for clarity's sake, I'll make sure that everybody can see properly. So, a square has four right angles and four congruent sides. So a square is where rhombus and rectangle overlap. Rhombus and square, and this is rectangle. Notice that I'm abbreviating a lot. So, rhombuses and rectangles are parallelograms. Parallelograms. Yeah, okay, I'm going to abbreviate that. And parallelograms are trapezoids. Trapezoids. And trapezoids are a type of quadrilateral. Quadrilateral. Lateral. Yeah, interesting Venn diagrams. Okay, find the missing measure in this quadrilateral. Hey guys, what's the internal angle sum of a quadrilateral? Well, we can cut it into two triangles, and all those triangles' internal angles would be part of the quadrilateral's internal angles, and they wouldn't overlap. Okay, that's 180 degrees plus 180 degrees, so 360 degrees. That means 100 plus 110 plus 60 plus x is equal to 360 degrees. So, if we subtract 160 to get 200, then we get 200 minus 110, which gives you 90 degrees. Yeah, so this angle x is 90 degrees. But it's marked as x degrees, so it's just x equals 90. Alright, let's classify these quadrilaterals using the names that best describe it. Well, this one, it has a right angle, but it has no particular equal or parallel sides. So this is just a regular quadrilateral. Quadrilateral. This one has all the sides equal. That means it must be a rhombus or a square. Does it have right angles? Do we see right angles? No, so this is a rhombus. Take heed though that even if you see right angles, unless they're labeled as such, it can get pretty dangerous to assume. I mean, unless you're thrown in front of a ton of rhombuses and some of them look like they have right angles, and be like, are these rhombuses or squares? Like, you have to label them. Yeah, then you can use your judgment. Here you have parallel sides. This, do we know anything about these side lengths? Well, we know that the opposite sides have to be equal because this is a parallelogram. Do we know that all the sides are equal though? No. So this is just a parallelogram. Okay. Find the missing angle measure in each quadrilateral. The internal angle sum is equal to 360 degrees, so 45 plus 135 plus 88 plus x is equal to 360 degrees. Therefore, x is equal to, notice that it says x degrees up here, not just this angle is x. It says this angle is x degrees. Therefore, we don't have to say x equals however many degrees. If it had just put angle A, or angle B, or angle x, then we would have had to say equals however many degrees. This is important stuff. Units. So, on this side, we have 180 degrees already. So 180 minus 88 is 100 minus 8, so 92 degrees. Wait, we already have a degree symbol there, so just 92. Now here, x plus 72 plus 82 plus 95 is equal to 360. Okay, then. How do we subtract this quickly? Oh, 70 plus 80 plus 90. And a 2 plus 2 plus 5. Well, the 2 plus 2 plus 5, that's a 9. Okay. 70 plus 80 plus 90 is 240, because 3 times 80. And this is going to be 360 minus 240 minus 9. So 120 minus 9, so 111 degrees, right? No, it's x degrees. So just x equals 111. Here, plus 125 plus 54 plus 96 equals 360. So, what's 54 plus 96? Oh, that's 50 plus 100. So 150. And 360 minus 150 gives you 210. 210 minus 125 is 200 minus 115, which leaves you with 85. And the degree symbol is already given for us. So let's consider what happens if you have the same shape but stretch it to be bigger or smaller, compress it to be smaller. So this symbol means is similar to. So if you have triangle ABC is similar to triangle DEF, that tells us that all the angles match up, or they correspond to each other. And the sides, the ratio of the sides is going to be the same. So basically, you stretch this shape by a factor of however much, all the sides are multiplied by the same amount, or all the corresponding sides. Because guess what, guys? You can flip this around or rotate it, and they would still be similar shapes as long as the angles correspond and the sides also correspond. Of course, they have to correspond in the same order. Yeah, that's kind of important too. Now let's say we know that these rectangles are similar. That means that the ratio of ST, so because MNOP is similar to RSTU, therefore ST over NO, ST over NO is equal to, I'm looking at the corresponding sides, ST corresponds to NO, so OP must correspond to TU. Or rather, we should say that TU corresponds to OP. We need to make sure that we're comparing the bigger shape to the smaller shape, or rather, one shape to another in the same order. Equals TU over OP. So that means 28 over 7 is ST over 5. ST must therefore be equal to 20. Wait a second, it says find the length of ST, so 20 feet. Yep. the line segment ST equals 20 feet. Exercises. Find the value of x in each pair of similar figures. Well, we're told that these are similar. So because ABC, triangle ABC, is similar to triangle DEF, please note that the similarity symbol, I've seen it written in both ways, like which end of the squiggle comes first, like up or down. So make sure you know how your area writes it. It's one of those funny things where conventions may vary. Yeah, okay, so that means that AB over DE is equal to BC over EF. Depending on preference, you may want to have EF or the specific side you're looking for as a numerator, because a lot of people seem to find that easier for some reason. AB is 3, DE is 9, BC is 5, and this is over x. So if you cross multiply, look, this is 1/3, guys. So if you cross multiply, that just gives you x equals 15. And units, it says 9 meters, x. It doesn't say x meters, so you have to put the units yourself. Now on this one, because triangle HIG, it's weird to see I actually being used as a point around here. Oh well. It's similar to triangle. Make sure that all the points that correspond are listed in the same order. KLJ. Therefore, KL over HI is equal to KJ over HG. KL is X, and HI is 2. KJ is 12 over HG is 4. So, X is equal to 6 feet. Now, here we have similar rectangles. Well, we're told they're similar at least, so we treat them as if they actually are. Now, we could say that, oh, this shape, when we're doing similarity, it was flipped over. Or we could just say, guys, they're rectangles. Therefore, this must also be 9 yards. So, because MNOP P is similar to RSTU, therefore TS over ON is equal to RS over MN. So TS is X over ON, which is 9 yards, is equal to RS, which is 10 yards, over MN, which is 5 yards. X is equal to 18 yards. Now, for this last example, we would have, because ABCD is similar to EFGH. Oh, how convenient. that the points are lettered alphabetically. Therefore, HG over DC is equal to HE over dA. HG is X, DC is 5 inches, and HE is 18 over dA, which is 6. Therefore, X is equal to 15 inches. Now, what is a polygon? A polygon is a closed shape that is formed by 3 or more straight lines. A polygon does not have lines that cross each other. So say this, yes, it's made of straight lines. It's closed because your pencil ends up where it started. But it's not a polygon because the lines crossed one another. Polygons can be classified by the number of sides they have. You have triangles, quadrilaterals, pentagons, penta means 5, hexagons, hex means 6, heptagons, hepta means 7, octagons, means 8. The most common type of octagon you'll see in North America is probably a stop sign, which is a regular octagon because all the sides are congruent and all the angles are also congruent. It looks somewhat like this, except all the sides are actually the same length. A nonagon has 9 sides and a decagon has 10 sides. And then after that, for our purposes, we don't bother with having special names for them. We say like 13-sided shape or 23-sided shape. If you have a polygon that is regular with an increasing number of sides, it will increasingly resemble a circle. However, no, a circle is not in fact an infinite-sided polygon, even if they would look the exact same. Now, the tessellation is an arrangement that's made by tiling a flat surface using one or more geometric shapes. There are no overlaps and there are no gaps. Floor tiling, whether it be simple squares, because come on, square tiling is pretty common, or rectangles, or even triangles, or hexagons, those are tessellations as long as they have no overlaps or gaps. Yes, I know that there is caulking and cement and stuff between square floor tiles, but details, guys. This is an example of a tessellation. There are 2 types of shapes here, 2 types of rhombuses. And, well, they fit together with no overlaps or gaps. It's actually possible to make pentagonal tessellations, but they aren't going to be regular pentagons because regular pentagons, they don't come together to form 360 degrees at any point. You have 108 degrees per angle within the regular pentagon. Alright, let's determine whether each figure here is a polygon. If it is, classify the polygon and state whether it is regular. If it's not a polygon, explain why. This, to me, it looks like a regular polygon. Yeah, it looks like a square that's just been rotated to be on its side. This is square. When you have specific types of special quadrilaterals, you generally just actually label them by their specific type. Regular. Or you could say regular quadrilateral, because a regular quadrilateral is a square. This is not a polygon because, well, you have lines that cross each other, or rather meet each other. You don't end up with your pencil where it started if you draw this all in one stroke. So this is not a polygon. A polygon. Lines meet at non-internal angle. No angle go sites. In a polygon, you only ever have two lines meeting at a time. So also multiple lines, multiple line segments meet. Yeah, in a polygon, you only have two line segments meeting at each vertex. Now determine whether each of these figures is a polygon. If it is, classify the polygon and state whether it is regular. If it's not, explain why. This one is a polygon. It's a simple closed shape where the lines don't cross over themselves or have more than two lines meeting anywhere. When two lines meet with an closed shape, it's called a vertex. So this is a triangle, obtuse triangle to be specific. Triangle. And it's non-regular. Non-regular. This shape is not a polygon, despite the fact that it is a closed shape, because it has a non-straight side. Non-straight side present. Okay. This one, it's a pentagon with all the angles equal and all the sides equal. So this is a regular pentagon. Pentagon. This shape here, it's closed and it doesn't cross back over on itself, but it's not regular. The angles and sides are not all congruent. So this is a 1, 2, 3, 4, 5, 6 sided shape. It's a hexagon. Hexagon. Non-regular. Regular. Alright, here we have a square which is regular. We could also say this is a regular quadrilateral. Regular quadrilateral. Quadrilateral. Whereas here we have a squiggle of a line. It's all straight lines, but this is not a closed shape. You don't end up with your pencil coming back to where it started. So, not non-polygon. And it's not closed shape. What happens if we have two figures that are congruent except we move one of them? Well, if we describe the position of the vertices of one of the figures on, say, a coordinate grid, we can say, oh, we moved it however many grids to some side and then how many grids up or down. Yes? So these are called translations. Now, a translation moves the geometric figure in some direction without turning, turning is rotation, or inversions or reflections. So there are no reflections involved. You don't flip it over or something. You just move it. When you translate a figure, every point of the original figure is moved the same distance and in the same direction. To graph a translation, move each vertex in the given directions and then connect the new vertices. For example, triangle ABC has vertices A, -4, -2, B, -2, 0, and C, -1, -3. Now, if you move it 5 units right and 2 units up, well, you can easily count the grids and then, oh, A prime. The apostrophe symbol, when you use it for, say, a point, you read this as A prime. And if you have B apostrophe, that's B prime. And if you have a double apostrophe, or on your keyboard or computer, you probably put the quotation mark. Actually, depending on country, that's called a double quote mark, I think. But I know that in, say, places like England, you go single quotes, and then in the middle, if you want to say something else that's quoted again, you use double quotes. Such as, Runza said, right, so you're saying, blah, 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 that part is in double quotes. Are you? Yeah, whereas in other countries, it's double quote mark on the outside and single quotes in the between. Okay, so actually, I'm not sure what you call this double quote symbol depending on region. It's just around here, I'm pretty sure it just gets called double quote. Oh well, the point is that if you have, say, A prime prime, you call it A double prime. All right? So, the vertices of the triangle, a translation of 5 units right. Hey, the x coordinate goes left to right. And left is negative and right is positive. So 5 units right means +5. So A, -4, -2. 5 units right and 2 units up means +5. And 2 units up +2. So you end up with A prime of 1, 0. Technically, this is not how you would write it in vector notation, but we don't want to overcomplicate things for now. We just think, hey, if we're moving it 5 units right and 2 units up, then we're doing this. Like, this is basically the equivalent of long addition version of how you add vectors to points, i.e. how you translate points. But I'm pretty sure you don't learn vector notation until way later, so we're not going to do that. Now for B, well, B is -2, 0. So 5 units right, that means -2 plus 5. So B prime is 3. And 0 plus 2 units up, 2. What about C prime? C prime is 5 units right from -1 is going to be 4. And -2 plus 2 units is -1. We have triangle RST here, which has vertices R2, 2, S3, -3, and T1, -1. Now we find the vertices after each of these translations, and then we graph the figures and the translated image. We only have one grid. That means we're going to be looking at R prime and R double prime, and S prime and S double prime. So, R prime is going to be at 5 units left from x-coordinate 2 is going to be 2 minus 5, or negative 3. And 2 units down from y-coordinate 2 is going to be 2 minus 2, or 0. And s prime is from 3, 5 units left, gives us negative 2. And 2 units down is negative 3 minus 2, or negative 5. And t prime gives us 1, and 5 units left from 1 is 1 minus 5, or negative 4. And negative 1 minus 2, so down 2 units, is negative 3. Our double prime is 1 unit right and 3 units up from 2, 2. Let's do one part at a time. All right, so 2 and then 1 unit right gives us 3, and 2 and 3 units up gives us 5. S double prime, that's from 3, 1 unit right, or 4, and negative 3 plus 3 is going to be 0. And t double prime is 1 plus 1 unit right is 2, and negative 1 plus 3 units up is 2. Okay, so let's plot these points. 2, 2 is R. S is 3, negative 3. You know what? Yeah, let's label the axes first. So this is 5. This is 5. I'm doing this so that it's nice and out of the way. O, the origin, is 0, 0, unless specifically marked otherwise, so we won't have to mark that point. So, 2, 2, 3, negative 3. That's over here. And 1, negative 1. Okay. R prime is, you know what, yeah, we should totally actually mark out which one is which first. Yeah, R prime is negative 3, 0. So negative 3 is 0. R prime. S prime is negative 2, negative 5. That's down here. And t prime is negative 4, negative 3. Negative 4, negative 3. So, this is S prime. This is t prime. And 1 unit right and 3 units up, R double prime is 3, 5. 3, 5. And t double prime is 2, 2. This is also t prime. And s double prime is 4, 0. Oh, okay. Now what do? We connect these points with straight lines, and that means you use some form of ruler. This is perhaps a little bit fancy, but it gets the job done. So some sort of straight edge. You could also use, say, the straight edge of a protractor, or even a straight sheet of paper. It doesn't really matter. You need some sort of straight edge to draw straight lines. Observe how we relocated the label for point R, which is the same as the point T double prime. This sort of thing happens reasonably often when you're drawing diagrams, which is why when you're drawing diagrams or graphing, you always start with a pencil. Even if you have to go over it afterward in pen, sure, whatever. But initially, when you're working on it, at least, always use a pencil. This way you can correct indiscretions. lines, or this looks pretty awkward here, or just oops episodes. Okay, so next, after we talk about just moving things, of course we have to do the desk flip meme. No, we don't. We have to start flipping them over. Okay, so if we have a figure that matches exactly when it's folded in half, that has line symmetry. What happens if you have two figures that have line symmetry across some line that may be between them or it may overlap with them? Like say if you have two triangles that overlap a little bit. Well, that could be because it was a reflection. It should be pointed out that some figures have more than one line of symmetry. For example, a square has, if you have a square that say looks like this, it has one line of symmetry, another line of symmetry, and then two diagonal lines of symmetry. If you have a circle, it has infinite lines of symmetry. Determine whether each figure has line symmetry. If so, draw all lines of symmetry. Well, this triangle here, it looks like an isosceles triangle. It looks like this half is the same as that half. So we would say that the line of symmetry is about here. Here there is no line symmetry. However, it has radiosymmetry. What is radiosymmetry? Well, that means if you have a section and you rotate it and you rotate it again and again, then all those sections are the same. So if you say cut this in half and rotate this side over to that side, oh, it has radiosymmetry. A type of transformation where you flip a figure over a line of symmetry is a reflection. And if you want to draw the reflection of a polygon, you find the distance from each vertex to the line of symmetry. The distance to the line of symmetry means perpendicular distance, i.e. right angle. Like say if you have this line and you want to reflect this shape, you would draw to the line of symmetry, the closest distance, which is perpendicular. You would extend it by the same amount, and there would be a point. And here also, there would be a point, and the same for your last point. These would all be perpendicular to your plane of symmetry. Now, in physics class, actually in like grade 10 science or so, in science class, at some point you will learn about plane mirrors. So this would symbolize that this is a plane mirror. It's a flat mirror. And that side is the solid side, the side that has stuff behind it. And your image would be found here. As you can see, it's advised to use a ruler or a straight edge whenever you are working with something that is allowing you to do so. Unfortunately, I'm not. So, you connect the resulting vertices to complete your reflected image. However, if you're doing a reflection over, say, the x-axis, what is the x-axis? The x-axis means it's where y equals 0. Okay, so if you go from 3 to 0, that's a distance of 3 grids, and then another 3 grids to the other side gives you just -3. So you just flip the signs of the y-coordinate if you're reflecting over the x-axis. If you're reflecting over the y-axis, you flip the signs of the x-coordinate. So, what are the coordinates? Well, A prime would be, the x is still going to be equal to 3, because reflecting over the x-axis, oh, that doesn't change where the x-coordinate is. But the y is now -3. B prime is 2, negative 5, and C prime is 0, negative 2. All right, exercises. For these, determine which figures have line symmetry. Write yes or no. If yes, draw all lines of symmetry. So this I here, we see that the two sides are the same. Okay. But we see that the top and bottom are also the same. Like they are symmetrical. Just flipped over. So reflected across the line of symmetry. Whereas this has no. It says write yes or no, so wait, yeah, we should probably write yes here as well. So there's no line symmetry here, but we don't have to write the whole thing because instructions. Reading instructions is very nice. You avoid mistakes and you can save effort. So, triangle ABC has vertices A, 1, 3, B, 1, 1, and C, 4, 3. Find the coordinates of the vertices of ABC after a reflection over the x-axis. Then graph the figure and its reflected image. Reflection over x-axis means just flipping your y-coordinates from positive to negative, or, well, just flipping the signs. Because if they were negative before, they're now positive. It's just the same amount, the same magnitude, the same absolute value. Okay, so A prime is going to be 1, negative 3. B prime is going to be 1, negative 1. C prime is 4, negative 3. Right. If we're going to graph this, A is 1, 3. B is 1, 1. C is 4, 3. And the corresponding points, B. As you can see, it can seem to be easier just doing this on a grid than doing this mathematically, because you can just look. Okay. Now we should apply the fabled implement known as, well, anything with a straight edge, really. So now that we have applied the straight edge to the graph, we're done. Yeah. You don't actually have to go do the ... show perpendicular to axis of reflection thing that you will eventually need to do for, say, science class when you're showing where you're plotting the reflection of a mirror. Yeah, there, when you're actually plotting the reflected image, you will need a ruler. Okay, that's actually it for this chapter. So, see you next chapter.